So let's talk about the curl and its interpretation. So for now you know how to calculate the curl, right? So you start with a vector field f of r. And you calculate the curl, and the result is another vector field, let's call it C of r, which can be calculated by doing the cross product between the nabla operator vector and the input vector field f, okay? Which, as you know, involves calculating the determinant. Where here fx, fy, and fz represent the x, y, and z components of the vector field f. So you know that we now can expand this determinant. I am not going to write down the equation again. It's written up here. When we talked about the curl, I expanded the determinant and we found that this is the curl. This is the answer. So it is a vector field because it has a x hat component, a y hat component, and a z hat component, which depends on x, y, z. Okay? So coming back here, we know how to calculate it. But now the question is, how does it look like? So remember that with the divergence and with the gradient, what I did was I showed you examples, but these examples were in 2 dimensions, because in 3 dimensions, it's not very pretty to draw vector fields. They look very ugly, okay? And this is a problem, because it means that I will have to calculate a curl of vector fields in 2 dimensions. But now comes a problem. When you are in 3 dimensions, your vector field f is a function of x, y, and z, a vector function of x, y, and z, which means that you have 3 functions, fx of x, y, z, fy of x, y, z, and fz on x, y, z. But now if I want to show you examples in 2 dimensions, I need to assume that we have a vector field in 2 dimensions, right? So it would look something like this. We have 2 components, the x component as a function of xy, and the y component as a function of xy. The problem is that if we now want to calculate the curl of this, curl of f, this would be the cross product between the nabla operator in 2 dimensions, cross product these 2 functions. Problem is that the cross product is not well defined in 2 dimensions. Okay, you realize the problem, right? I cannot write now the determinant because it would be 2 columns and 3 rows, so it doesn't make any sense. So what we have to do is we have to do a trick which sometimes is called the 2-dimensional curl. So what we do is we just assume that we consider a vector field which is defined, which is a vector in 3 dimensions, but only has an x and a y component with a 0 z component. Okay, so we can kind of assume this, and therefore if we now want to calculate the curl, we calculate it for this 3-dimensional vector field. Okay, so we do this operation, and 0. Okay, now if I write the determinant for this, let me write it here. So as we have seen, we can assume that fz is 0, but not only that, notice that our functions f of x and f of y, they depend only on x and y because we are describing a 2-dimensional field. They do not depend on z. Therefore, what's going to be the partial with respect to z of fx? It's going to be 0, right? And the same with the partial with respect to z of fy is also going to be 0, because the functions do not depend on z, or in other words, they are constant with z. Therefore, whenever we have to calculate a partial derivative with respect to z, that's also going to be 0. Which means that we kind of get rid of these two slots in the determinant, which means that when I calculate the cross product, I get x hat times 0, because I need to calculate this determinant in which one column is all zeros, so it's x hat times 0, plus y hat times 0, because again I need to calculate the determinant of this small matrix in which one column is all zeros, plus z hat times this determinant, which we can calculate as partial fy with respect to x minus partial of fx with respect to y. Okay, so you notice that when we do the curl on a two-dimensional vector, we kind of do this trick of assuming that we actually are working with in reality we are working with a three-dimensional vector, but we are assuming there's no z component, and we are assuming that the vector field does not depend on the z axis. Okay, let me visualize this. So our situation 1 and our assumption 2. So let me visualize our situation 1 is just a vector field defined in 2 dimensions. So for each point, we have some sort of vector which depends on position, right? This is what we want. We want a 2-dimensional vector field. But now we are assuming a 3-dimensional vector field which has a 0 z component and which doesn't depend on z. So what we are assuming is something like this. If we imagine that we constrain ourselves to the xy plane, we have our vector field here, which is the original one. And these vectors never go outside of the xy plane. They are always contained in the plane, right? Because they are representing our 2-dimensional vector field. But now we are kind of assuming that this vector field is replicated, so we can copy this plane. We can now replicate it at every value of z. Okay, so for every single value of z, you can kind of copy that plane. Let me actually copy it, literally. If I do like this, duplicate, duplicate, duplicate. Now I remove the axis. Very good. So this is what we're doing. We're kind of replicating the vector field at every value of z, and now we're calculating the curl of this. And the curl of this 3-dimensional vector field turns out that it only has a z component. Okay? So this is the trick that we do for calculating the curl in 2 dimensions. Now, sometimes what the interpretation for this is that a vector field in 2 dimensions, we apply something called the 2-dimensional curl, and the result is a vector field that has only a z component. Okay? In other words, we can interpret this as being a scalar field. Because what's the difference between a vector that only has a z component or a scalar, right? Mathematically, we can consider this as our scalar output, so that when we have a 2-dimensional vector field as the input, we apply this 2-dimensional curl, and our output is just a scalar field. Or in other words, it's just a curl which only has a z component. Okay? So that's what we are going to do in order to plot some examples. So the simplest cases to interpret the curl, you already saw that YouTube video that I suggested that had beautiful visualizations, but let's focus on the simplest cases. So if your vector field f, which is the input to the curl, seems like it's like a fluid rotating around a point, then this point will have a curl, and the direction of this curl will follow the right-hand rule. Okay, so in this case, if you use your right hand, and you rotate with your fingers in the direction of the vector field F, your thumb will be pointing in the direction of the curl. So in this case, my thumb is pointing into the paper, which means that this is the negative z direction, right? Because the z-axis is coming outside of the page. So therefore, the curl of F calculated at this point is negative. Now, if the field seems to rotate anti-clockwise, then you use your right hand, your field F goes anti-clockwise, and my thumb is pointing outside of the page. Okay, so this means that the curl at this point is positive in the z direction. So the z component of the curl is positive. While in the case in which there is no net rotation around a point, then the curl is 0. Okay, these are the very simple cases, but there are other slightly less simple cases. For example, when the vector field is stronger on the top than on the bottom, then there is still some rotation, right? So if you imagine you place a windmill, like I drew here, you placed a windmill here. This windmill is being pushed stronger on the top than on the bottom, and therefore there is still going to be a net rotation of the windmill. In this case, it's a clockwise rotation, meaning that the curl is directed along minus z. So the curl at that point will have a negative z component. While if the field F is stronger on the bottom than on the top, then if you imagine a windmill placed here, this windmill is being pushed stronger on the bottom than on the top, and therefore there will be a net torque which will cause it to rotate anti-clockwise, which is associated with a curl in the positive z direction out of the paper. Okay, so these are less trivial cases of non-zero curl. Let's use a Mathematica applet to actually plot the curl of some vector fields. So here you can see on the left I am plotting a vector field, and this vector field is given by this function here. So this function here is a half of the exponential of minus x squared minus y squared multiplied by the vector minus y comma x. So this is the x component and this is the y component of the vector field. And this looks like this nice whirlwind which decays exponentially as we get far away from the origin. Okay, so this is the vector field which is plotted on the left, and this will correspond to my input vector field in 2 dimensions. Now on the right, I'm going to plot this output curl, which only has a z component, and therefore I'm going to plot it as if it was a scalar field. Okay, so I'm going to use a color map in order to plot the curl. So that is what I'm showing on the right-hand side of this figure. So you can see the color bar here. So 0 is white, plus 1 is blue, and negative values are red. So what you can see is that there is clearly a positive curl, because if you apply your right-hand rule, so the curl is going in this direction, the field is going in this direction, so the curl is pointing out of the paper, right? So this is pointing out of the paper, so it corresponds to a positive z curl. But it's interesting to notice that there is a ring here of red region of the curl. So why is that? Because even though a windmill placed in any of these positions will rotate anti-clockwise, if you place a windmill out here, that windmill will feel a force that is stronger in this side than on the outside, and therefore it will rotate clockwise. So you can see that the curl is indeed changing from positive z to negative z as we get away. Okay, so it's very interesting to see how subtle the curl can be. Now here I can change my function. So consider this other function. So this other function is written like this. So the x component is y times the exponential of minus x squared, and the y component is x times the exponential of minus y squared. Don't worry about this, I just plotted it. So this is how the vector field looks like. And then I calculated the curl in Mathematica and plotted it as a scalar field. So this represents the z component of the curl. So now notice that in these blue regions there is an anti-clockwise rotation. So any windmill that you place anywhere here or here will rotate anti-clockwise, and I think it makes sense. While any windmill that you place in these 2 regions will clearly rotate clockwise because it's being pushed stronger on the top than on the bottom, so it will rotate clockwise. And you can see this as the red region, right? Let's see another example. So this time I have this function here. So you have the x component is x plus y divided by the square root of x squared plus y squared, and the y component is minus x divided by the square root of x squared plus y squared. And you get this nice twist thing, and you can see that the curl is mostly negative because this is associated with a clockwise rotation, so that the curl is pointing in the negative z direction. But the curl is stronger here than here. So this kind of makes sense that here the curl will be stronger than here. Even though the field is stronger here, it's more homogeneous here. It's not rotating as much as it is rotating here, right? So try to get some intuition for the curl. Another example is this ugly expression, which I'm not going to read out loud, but it produces this beautiful vector field pattern. And you can see that you have regions of negative curl here, positive curl here, and then here you have positive and positive and negative and negative. Yeah. So you can imagine placing a windmill at each of the points in the xy plane, and the direction and speed of rotation is codified into the curl. Okay. Finally, one last example. This is an example of a very simple vector field, which is x plus y in the x hat direction and x minus y in the y hat direction, which looks like this. And if you calculate the curl, it is exactly 0 everywhere. So this means that when you place a windmill at any point here, it will never rotate. Even though it seems there is some kind of rotation, it's always compensated. Okay? So this is a case of a field that has no curl. Okay, so I hope that was now clear, and that now you have a clear interpretation for what the curl is in every different case. Okay, thank you very much. See you in the next video where I will expand on three-dimensional curl.